In this video, we're going to talk about fluids. So we know that fluids take the shape of their containers. They include liquids and gases. And you read about that in your book, The Difference Between Solids and Liquids and Gases, and you probably learned about it a long time ago. We're going to be using pressure a lot. Pressure is force divided by area. It is a scalar quantity. And the force due to a fluid's pressure is going to push not only on the walls of the container, which that happens perpendicularly to the wall, but also on the fluid itself. So if you think about having a bucket and you punch a bunch of holes in it, the water is going to shoot out of the hole if the bucket is filled with water. And the reason the water shoots out of the hole is because the pressure from the water behind it is pushing it out of the hole. You'll also notice that when we have holes towards the bottom of the bucket, that water is going to be shot out farther than holes towards the top of the bucket. You can see like this one only goes like this, because the pressure is greater at the bottom than it is at the top. And you learned about that in your lab. We'll learn about it more in this lecture. The origin of pressure is the gravitational field force on the fluid. So if the fluid is suddenly in space and orbit around the International Space Station where there's no basically normal force on it, then you are not going to have this fluid pressure. Pressure is a scalar, like I said. The unit of pressure, the SI unit, is Pascal, which is a Newton per meter squared. And then we also are going to be using density. Density is mass divided by volume. You should already know that. The symbol we use for density is a Greek symbol called a rho. It's kind of like a curvy P. That's how I make it. This is how it's typed in this particular program. The unit for that is kilogram per meter cubed. We will also be using kilogram per liter quite a bit as our unit. So it's important to understand that when, like at first we're talking about static fluids, so the fluid is not flowing, it is just stationary. Now the particles, you know, like the atoms, the molecules are not actually stationary, they're bouncing around off of each other, but the fluid as a whole is not flowing. So, you know, like a beaker of water is stationary, but a river would be flowing. So we're talking about static fluids first. If we think about a particle in this static fluid, the pressure is the same on all parts of the particle. And this is kind of weird. I think that it makes a lot of sense that there's pressure downward on this particle because there's this weight of all this water above it. But it's kind of weird to also think that there's pressure upward. The same amount of pressure downward is also upward, and to the side, and at this angle. So all of these pressures are the same. If the pressure were not the same, the fluid would flow. So we know the pressure has to be the same from every direction on a particle in the water. I tried to change that to red and it's not letting. There we go. So we also know that if the fluid is at rest, it will always provide a perpendicular force on the containers of on the walls of the container or any surface that it's up against. So let's talk about the equation for pressure at a certain depth in a fluid. This is called hydrostatic pressure. So the hydro is basically means water, but it works for any fluid. Static means the fluid is not flowing, and then we have pressure. So horizontal forces are going to cancel each other out. And so we're not worried about horizontal forces. We're just going to think about vertical forces. So the pressure on a particle of water is due to the weight of the water above the particle. So it's a good way to think about how to derive the equation. So if we think about this little particle right here in the water, we are thinking about the weight of the water on top of it. So this is super annoying that it's not letting me choose my pens. Okay. So we have this column of water right here on top of this particle. Sorry, this is such a bad drawing. So this is the water. And our net force has to be 0 because it's a static situation. So the force up equals the force down. We know that our force up is going to be forces pressure times area. So it's the water pressure times the area of the particle. The force down is going to be the weight of the water, which is mg. And then also we have to add the atmospheric pressure. So this is kind of annoying that I have to keep switching this, but okay. So this is the air above it. So we have another column here that is the air. So this column that goes all the way up to the top of the atmosphere. And this is air. So the weight of all of this stuff, so gravity is pulling all this stuff down towards the center of the Earth. The weight of all of that stuff on top of this particle is what causes the pressure. So now let's look at this equation a little bit more. We know that volume is equal to area, so the area of this little circle, this little particle, times the depth. So we're thinking about the volume of water here. This is the depth of the water. And then you have the volume, the area of that circle, or whatever part, the area of the particle, the cross-sectional area. We know that mass is equal to density times volume. So if we take this and we solve for volume, we get volume is equal to mass over density. And then we're going to plug that into, oops, I drew the arrow the wrong way. You plug that into here, and you get mass over density. Oh my goodness. Okay, I'm just going to use this pen. Mass over density is equal to area times depth. And when you solve for mass, you get mass equals area times density times depth, or I put density, area, depth. Either way it works. So then you plug this into here, and then you get this equation. Pressure times area equals, the P naught is atmospheric pressure. Let me put a little note about that over here. Oh, I think I have a, yeah, I definitely put a note. Oh my gosh, that's not useful pressure. Okay, so P naught is atmospheric pressure times area times density of the fluid times area times depth times G. You should notice that our areas all cancel. And then we are left with the equation pressure, which is the pressure of a liquid at depth D is equal to the atmospheric pressure, so the air pressure, which it's good to say atmospheric pressure or air pressure. Usually it's atmospheric pressure, but sometimes you could have a situation where this would be the air pressure if it was like a closed container, where there was more air pressure than atmospheric. And then that's equal to density times depth times gravitational field strength. So if you think about things that will increase your pressure, the density of the fluid would increase your pressure, the depth would increase your pressure, or the gravitational field strength, or the atmospheric pressure or the air pressure above it. This should make sense to you if you've been swimming in a swimming pool. You can feel pressure quite well with your ears. So if you dive down in the swimming pool, you feel more pressure in your ears. You might feel the need to pop them, which is when you let little bits of air in and out to equalize the pressures. And that should make sense to you. So some other key points. If we have a difference in pressure, that's going to cause the fluid to flow. And we're going to study that soon. But right now we're just going to talk about static situations. The air pressure is going to be the same on, oh, I'm sorry. I was thinking about this thing. Okay, so let's say that we have this thing, and I have one of these kind of like this in my classroom, and we fill it with a fluid. When you fill it with a fluid, they are all of these tubes, no matter what shape they are, since it's a connected fluid, they're all going to end up at the same level. So some people think that maybe the skinny one will be higher, or because you have a bend in it, it might affect it, or the bulge, but they're all at the same level. The reason for this is that if there's a difference in pressure, the fluid's gonna flow. We know that the air pressure is the same on every surface because they're all exposed to the atmosphere. So we just have atmospheric pressure is the same at every surface. The pressure is only dependent on the depth and the depth at a certain point. So if we're thinking about the pressure right here, we only worry about the depth, right? We don't worry about the area because the area cancels. So this part doesn't matter. How big the tube is does not matter. It's not going to affect the pressure at all. So that means that at any point at the same depth, the pressure has to be the same. And so that's going to, because it's all a connected fluid. So if we had all those blue X's would be the same pressure. These green X's are all the same pressure. If one of them was higher, so like if this one was higher, the depth above the blue or the green X would be more. So you'd have more pressure at these places, which would cause the fluid to flow this way and go up higher in these until they all leveled out. So if it's just static, it's going to go to the same level. Let's do an example problem. And here we have a tube of water that goes down like this, and then it ends in this closed end. And I want you to tell me what the pressure is at this point right here, at that red star. So you can pause and give it a try for yourself. We do know that pressure is dependent on depth. So if this is a continuous connected fluid, so these along this line right here are going to have the same pressure because they're at the same depth from the surface. It doesn't matter that this is up against a wall. It seems sometimes like this should have more pressure, but it doesn't. If it had more pressure than this point, then it would like push along here and it would flow until they were the same. So we start off with our equation. Pressure equals air pressure plus density of fluid times depth times gravitational field strength. Our air pressure, oh, you know what? I feel like I missed that. Oh yeah, I didn't say it. It's written right here. Air pressure, atmospheric pressure at sea level, which is just what we'll use for our problems, is 1 atm, which stands for atmosphere. The SI unit is kilopascals, so, or pascals, but it's 101.3 kilopascals is the pressure of the atmosphere. Okay, so then we plug in our atmospheric pressure, which is 1.013 times 10 to the 5th pascals, because we have to get from kilopascals into pascals. Then we multiply by the density of water, 1,000 kilograms per meter cubed. You multiply by the gravitational field strength, and then you also multiply by the depth, and the depth is 0.6 meters, since this whole thing is 1 meter and this is 0.4. So you end up with 1.071 times 10 to the 5th pascals as your pressure. A little note on the density. A lot of times in science we use like grams per milliliter as our density of water, but since we're using gravitational field strength in newtons per kilogram, we need these units to work out. So we have, let's do a little unit thing down here so we can see what the units are. We have kilograms over meters cubed times newtons per kilogram times meter. So we can easily see that our kilograms are going to cancel. And then one of our meters cancels. Oops, that becomes 2. And then we get newtons per meter squared, which is the unit of, that's a Pascal, unit of pressure. So that works out. Okay, one more quick thing here is about gauges. So if you measure the air pressure in your tires, or really any air pressure measurement that you are given the difference in pressure between the atmosphere and the tire, the thing that you're measuring. So this is called a gauge pressure. It's the pressure difference between the atmosphere and the thing you're measuring. Because we can't really measure, it's hard to measure an absolute pressure. So to get an absolute pressure, or the actual pressure of your tires, you would have to take the atmospheric pressure and add it to the gauge pressure, because the gauge pressure is equal to the actual pressure of your tire minus the pressure of the atmosphere, since it's a difference in the two. So if you add the pressure of the atmosphere to the other side, you get that your pressure is equal to your atmospheric pressure plus your gauge pressure. Okay, that is all.